All right, so there's one kind of strange integration by parts example. It's a classic example, but it's very strange, and I wanted to just go through it because you don't actually end up integrating this directly, which is just really weird. So here's the example I have in mind. It's pretty famous. There's other ones that work similarly. E to the x cosine x, you'll see work similarly. Turns out you can do integral of sine squared or cosine squared. This method I'm about to show you. So here's a problem. E to the x times sine x. We're going to find the antiderivative of that. It's a product of two different types of functions, an exponential function and a trigonometric function, and that suggests use integration by parts. It turns out it doesn't really matter which one we pick, so let's just do u to the x is u is e to the x, dv is sine x dx, du is e to the x dx, and then v, antiderivative of sine, is minus cosine x, right? So that's our setup, and we do this, and we get u times v, which is negative e to the x cosine x, minus the integral of v du. The minus minus makes a plus, and v du gives us e to the x cosine x dx, right? So have we made progress? Because the whole point of integration by parts was to start with something hard and turn it into something easier. And this looks exactly as hard. So you don't think you made any progress, but let's go with it and kind of try again. Before I do that, I want to give this a name. I want to call this original integral I. And let's give this a name. Let's call it I1. Okay, so we want to find I1 now. So I1 is the integral e to the x cosine x dx. Let's play the same game. U is e to the x. dv is now cosine x dx. By the way, you got to be really careful here. If I had chosen now u to be cosine x and dv to be e to the x dx, then that's like up here. I mean, that's the two things you end up with up here. And when you go do an integration by parts, you'd get back to here and you get back where you started. And so you would have nothing. So I want to keep the same choice of u to keep pushing forward. So you got to be careful about that sometimes. But then, okay. So that's just a caveat, but there we go. There's that. And now v in this case is sine x, because antiderivative of cosine is just sine. So we get u times v, e to the x sine x, minus the integral of v du, which is e to the x sine x dx. Right, we have the e to the x here and the sine x, and I just put them there and then put the dx at the end. Okay, so again, doesn't look like much progress, except this is actually the integral we started with. This is I, right? It's the same integral, which you might think is weird. I mean, maybe it makes sense, right? We do this twice kind of because sine just becomes cosine, cosine becomes sine. We get back the same integral we started with. Maybe it doesn't even seem like progress at all, but let's actually plug in this formula right here, and we will get I in terms of itself, which is the thing that's kind of crazy, right? We have I equals this, and we have I1 equals that. And so let's plug that in, plug back in. So I up here at the top is this. I'm going to use this formula and then plug in for I1 right there. So that's minus e to the x cosine x plus I1, which is e to the x sine x, minus I. And now this is kind of crazy because, right, we have I equals something minus I. Let me just kind of write this schematically for a second. We have I equals all this stuff. I'm just going to write blah, all this, and then minus I. And so we could add I to both sides. And we get that 2I equals the blah. So I is 1/2 of the blah, whatever that was. And so we've now solved for I. Just by integrating by parts twice, we got the same integral back with a minus sign. But that minus sign right here was good because it let us add it over to the other side. If it had been a plus sign right here, that would be weird because the i's would cancel and you would lose all touch with I. In fact, I claim if you did that, somehow this would cancel too, because you'd just get like 0 = 0, which doesn't tell you much. But getting the I with a minus sign here is what's kind of the magical thing. And so thus we can see that I, which is the integral we wanted to find, let me just write that integral again, e to the x sine x dx, is 1/2 of this stuff up here, which is a minus e to the x cosine x plus e to the x sine x. I guess I should write plus c. And so that's kind of amazing that we somehow integrated without ever directly integrating e to the x sine x. We integrated twice, got the same thing back, and then, wow, somehow we the integral fell into our laps, or the antiderivative fell into our laps. It's kind of amazing. By the way, you could rewrite this a little bit. I mean, it might be nice to rearrange these terms to have a plus term minus a minus term. Or you could factor out e to the x. So you could rewrite this as 1/2 e to the x times, what is it, sine x minus cosine x, if you want, plus c. And then don't forget to check. Check that if you differentiate this, you actually get, if you differentiate this final answer right here, or in this form, whichever you prefer, that you actually do get back this. It's not super obvious. But there's some product rules going on. There's a product rule here, so but I think it's worth trying to check. So, okay. So it's strange, but it will come up again a few different times, and I wanted to show it to you. So, okay, I will stop.